Hi everyone, welcome to my channel. Myself Praveen Kumar. Now I am going to discuss about the internship on embedded systems which was presented by Emerging Information Technologies. Let's get started. Now we are going to discuss about the embedded systems, microprocessor versus microcontrollers, MIcroWave as an embedded system, requirements of the project, architecture of PICSIM lab, internal architecture of PIC16 F877A, project demonstration and learning outcomes. I am learning some topics during the time of internship. They are C data types, condition structures, and operators in the first week. Then arrays, pointers, functions, storage classes, and preprocess in the next week. And in the starting of third week, I have learned about the embedded systems and the microcontrollers. In that week, as I learned the microprocessors versus microcontrollers. In the fourth week, I have learned about the MP lab, IDE, PIXIM lab, and XCA compiler, and some introduction to CLCD and interfacing CLCD. Embedded systems. Basically, we can say embedded systems is a combination of hardware and software, but it is in general definition. According to the theoretically, we can say an embedded system is a computer system, a combination of a computer preprocessor, computer memory, and input or output peripheral devices that can as a dedicated function within a large mechanical or electronic system. Or we can say in other words, an embedded system is an isolated system specially designed to perform a designated function with the help of its hardware and embedded software. Embedded system structure diagram. In terms of hardware, a basic embedded system would consist of the following elements as sensors, analog to digital converters, processors, digital to analog converters, and actuators. Sensors. Sensors mean sensors that can sense the physical data, and it will send it to the and it will convert it to the electrical signals, analog to digital converters. It will collect the data from the sensors as electrical signals. Electrical signal means analog signals that will collect the analog signals from the sensors and convert it to the digital one process. The digital data which was collected from the A to D converters is processed in the processor. It was the heart of the microcontroller. Digital to analog converters change the digital data from the processor into analog data. They will collect the physical data from the microcontroller or processor and convert into the analog data, where it can given to the actuators. Actuators compare actual output to memory stored output and choose the correct one. We can see here diagram which was the CPU is the processor, it is the heart of the microcontroller, and it was given to the software memory D2A converters, auxiliary system power or cooling diagnosis part, human interface A to D converters, flags, ASCIIs, GPRs, ports, etc. And here sensors, it will collect the data, electromechanical backup and safety to actuators to external environment or sensors. Actuator, we can say sensors and actuators are the transducers. Sensors, they will convert the physical energy into electrical energy, as actuators convert the electrical energy into physical energy. Categories of embedded systems. Embedded systems are classified based on their performance and functional requirements, as well as the performance of the microcontrollers. The classification can be further divided into categories and subcategories. When classifying embedded systems based on performance and functional requirements, embedded systems are divided into four categories: real-time embedded systems, standalone embedded systems, network or networked embedded systems, and mobile embedded systems. We can see the architecture of the embedded systems and some examples. In block diagram we can see the SPI, UART, USB peripherals, I2C, processor is the heart, A2D and DAC, DA2A converters, PWM timers, and PIC16 microcontrollers have the internal oscillators, and this all work on the user. And we had a GPIO controllers, clock, and a DBG interface, sa- and catch files. Now we can see about the difference between microprocessor and microcontroller. Microprocessor contains ALU, GPS, PC, SP, control and timing circuit and interrupt circuit. As microcontroller is contains microprocessor in built-in ROM, RAM, IO ports and timer and counter circuits. It has microprocessor has many instructions to move data between memory and CPU. But in microcontroller we are only having few instructions to move data between my memory and CPU. Accessing time for memory and IO devices are more in the microprocessor. As we are having the internal memory microcontroller we can access the memory in a small time when compared to microprocessor. Microprocessor based system requires more hardware, where microcontroller based systems require less hardware. Microprocessor based system is more flexible in design point of view. Microcontroller based system is less flexible in design point of view. In microcontroller we are having less number of multifunction pins. In microcontroller we are having more number of multifunction pins. It is a key point for microprocessor and microcontroller. A single board CPU is called as microprocessor. A single board computer is called microcontroller. Whereas in microcontroller there will be only some ports to connect with the external devices. In microcontroller we are having the so many ports which can act as, or we can say as IO ports. Input and output ports are more in the microcontroller. Micro Microwave oven as an embedded system. Microwave oven is an electric oven that heats and cooks food by exposing it to electromagnetic radiation in the microwave frequency range. We can say the microwave oven is a household appliance that has revolutionized modern home kitchen. Microwave oven are so quick and efficient because they have cha- channel heat energy directly to the molecules inside the food. For the project, we require some knowledge in embedded in C, MPLAB IDE, XC8 compiler, PICSIMLab simulator, PIC16 F877A microcontroller, 16 into 4 CLCD tactile switch, MKP matrix keyboard, and timers. Now we can see the PICSIMLab architecture. PICSIMLab is a real-time emulator of development boards with integrated MPLAB X or AVR GDB debugger. It supports several devices that can be connected to the board for simulation. We can see here some are the outputs of outputs for fixed 16 F877A. They are like LEDs, SSDs, and GPIOs, I2C, or EPROM matrix keyboard, and some inputs like buzzer, CLCD, ADC, temperature sensors, RS232, etc. It is the basic model of the PICSIMLab simulator. When we open the application, it will be look like this. Here we are having the keyboard, LEDs, buzzers, and we can observe the processor, and we are having the screen. PIC16 F877A microcontroller. It was developed by Microchip Technologies for the use in a high pin count, high density, and complex applications. PIC, the PIC16F microcontroller offer cost efficient solutions for general purpose applications written in C that use a real time operating system RTOS and require a complex communication protocol stack such as TCP, IP, CAN, USB, or ZigBee protocols. PIC16 F877A is a 40-pin PIC microcontroller designed using RISC architecture manufactured by Microchip and it is used in embedded projects. It can be operated in the range of plus 4 to plus 5.0 volts at the speed from 4 megahertz to 40 megahertz. Now we can see some features of the PIC16 microcontroller. It has 35 instructions. The program memory addressing is up to 14 KB, data memory addressing up to 256 KB. We can operate the PIC16 microcontroller in the range of 4 megahertz to 40 megahertz up. It has 33 IO pins and 5 IO ports. It has a interrupt priority structure. In this we are having two 8-bit timers or controllers and one 16-bit timer or counter. It has 15 interrupt sources. We can operate the microcontroller in the range of 20 megahertz, like 200 nanoseconds instruction cycle. It is the pin diagram of the PIC16 F877A microcontroller. Here we are having the 5 ports, and each pin is multiplexed pin in the PIC16 F877A microcontroller. Here we are having a port A with from pin 2 to pin 7 and port B from pin 33 to pin 40 and port D from 27 to 30 and 19 to 20. Port C from 23 to 26 and 15 to 18. Port E from 8 to 10. And we are having the VDD, VSS and ground. This is the internal architecture of the PIC16 F877A. Where we are having the 5 IO ports, internal bus architecture. We are having the working registers, instruction decode and control status registers, multiplexer, file select register, address multiplexer, RAM file registers, program counter, program memory, and instruction registers. This all are pipeline. This is a pipeliner structure. CLCD. CLCD is defined as a character liquid crystal display. Is the most basic form of an electronic display device which is widely used. The main advantage of using a CLCD instead of 7 segment display and other multi-segment LEDs is that there is no limitation in display special and custom characters, animation and so on. Most importantly, the module can be interfaced much easily, unlike other modules with no complexity in both hardware and software. There are two types of display: 16 into 2 display or 16 by 2 display or 16 by 4 display. ASCII characters and some special characters are displayed. It is a widely used display in embedded projects. By using this, we can communicate in two modes as a 6-bit mode and 8-bit mode. It consists of the two registers, command register and data register. Matrix keyboard. A matrix keyboard is a small, compact input device that accepts user inputs and processed by the microcontrollers. A matrix keyboard is the kind of keyboard you see at microwave ovens, gas pumps, and calculators. It consists of a number of tactile switches arranged in a row and column format. The advantage of MKP is that use of it will allow the programmer to reduce the number of pins to be. In this diagram, we can observe there are 16 switches, and we can see the pins R1, R2, R3, R4, and C1, C2, C3, C4. By clicking the switch S1, the R1 and C1 will be high, and others will be low. As like we can if we switch the S11, the R3 and the C3 will be high and remaining will be low. Like that, this board will be work. Now we can see the project demonstration. After demonstration of the project, we can go to the learning outcomes which I have learned in this project and internship. That they are I got good depth knowledge about the internal working of the embedded systems, and I have known about the programming and domain skills, and some introduction to the softwares and interfacing the units. Real-time experience exhibited better problem-solving skills by analyzing issues to the challenges. Good exposure in standard industry practice of software development. I thank I heartfully thank the MRZ for making me learn these embedded systems and basic programming and domain skills, and an introduction to some software along with the interfacing unit. Thank you.